Hi everyone and welcome to another video of CS202 Online. Today we're going to wrap up talking about linked lists by introducing doubly linked lists. So what are doubly linked lists? Well, as the quote there says, it's twice the links, which is double the risk of having segmentation faults and problems. Well, not necessarily, because hopefully today we're going to cover all the potential things that you should keep an eye on when you're creating these doubly linked lists. So let's go ahead and jump right into it, okay? So let's first refresh what a singly linked list is, which is what we have been working on for the last couple of days. And so a singly linked list is made up of a bunch of nodes that are linked together. And so our node class has two main components, and that's going to be the data component and your link component, which is a pointer, right? And that pointer points to another node, so it's a node pointer. And then it points to other nodes, and that's how you make that chain or that linked, right? Linked list. And so on, okay? So the cool thing about the linked list is that you can insert things in the middle and in the front or behind and not have to copy things over versus an array. However, like you saw when we actually implemented the singly linked list, you really can't go backwards on it. You can only go in one direction, which is this way, right? And the only way that you can like print, for example, a singly linked list backwards is through the use of a stack or recursion, which is what we did, recursion. And so, you know, that's okay to use recursion. It's a nice example of it, but there shouldn't be a need for it, you know. There should be a way that I can traverse these things back and forth without it being a headache. Particularly, you know, when we were inserting things at the end of the list, we had to first traverse all the way to the end or second to last, and then we had to keep two pointers, one for the one before and one for the one after. It's a little bit messy, right? And so why not just take the idea of links, and instead of just linking to the next node, why don't we also link to the one before it? And so that is how doubly linked lists were born. I just realized I had my headset on, so I'll need it. So yeah. So that's basically what a double linked list is. It's going to be a node that is going to contain not just the data component and your link component here, but it's also going to contain another link component on this side. So two links, one data. On this side, I'm going to call this the next component, which is going to be what we've been doing so far, put into the next node. But over here, this link component, which they're both pointers, they're both node type pointers. So node pointer is going to, guess what, point to the node before it. And so now you can go in both directions. And that's really all there's to it. Like, that's it. That's doubly linked list. 4 minutes in the video, we're done. I mean, really we are actually, but what I'm going to do now is I'm going to go ahead and, code one for you. And also I want to talk about sorted linked lists, which if you saw the last video, which I hope you did, I said that I was going to talk about. So we'll code a sorted doubly linked list. That way, you know, two birds, one stone kind of thing. So here I have a prettier looking version of this. And so let's just really quickly make sure that we understand how this is going to look like once we link them together. So let's just go ahead and shrink this like this and just link these up together. So what if we have, say, another node like this that we're putting together? The trick here is that this is going to go and be linked both. Over here, this node is going to link to the next one, but also you need to make sure that you take this pointer and link it to the prior one. So the process of inserting is going to change. So if I want to insert a node, into my existing linked list. So the first thing is when you create a node, you want to also set both pointers to null, right? So not just one, but both. That's a good thing to do because like it ensures that that you don't have any issues later on, just like before. Okay, let's try to insert this at the beginning. At the beginning, it's pretty easy because all we got to do is just basically bring this down. And, you know, we have a head pointer. And now the tail pointer is actually more useful because now you can actually, like, move back and forth. So the tail, you know, if you want to reach the second to last item, just go to the tail and then move one, right? So the tail is actually, like, more viable now. The next thing is, like, if I'm going to go ahead and put this in here, I got to update this pointer to point here. And then I got to take this previous pointer and make it point to the node that I'm inserting, right? So that's two pointers that I'm updating. And then over here, this can stay to null, but you got to make sure that you move the head, right? Okay. Now, what if the one that I was inserting was actually the one in the middle? Okay. So if it's the one in the middle, I got to update 4 pointers. So I start with this, right? And so what I need to do if I want to insert it between those two nodes is I gotta make the space for it. Well, here, let's just say it's like this. So what I'm gonna do is, and I gotta have to again have this pointed with something temporarily, so we'll call it the temp pointer. So I'm gonna take temp next, and I'm gonna make that point to the new node. What that's gonna do, not new node, to the next node, sorry. What that's gonna do is gonna make it point there. Okay, now where is this currently located? Well, it's currently located over here. So H next was pointing here, right? So I'm basically copying that one. So I'm copying this one right there. That's step 1. Step 2, go ahead and take this node's previous pointer. So that's going to be this one. And make it point to the node that you just created. So that, okay? Once you do that, you can, obviously this gets updated. You can now go ahead and take your temp node previous pointer, which is this one, and make it point to the node before it. That's the third update. Finally, the last update is to take the current node's next pointer and make it point to your new node. So that's 4 pointers that you have to update. And again, you want to make sure that you're updating these ones first before these ones so that you don't accidentally cut off like links, right? So what I'm saying is, if you have something like this and you have your new node, and the first thing you do is you take this pointer and make it point there, well, you just lost access to this stuff. So big memory leak and also just fail in general, right? So that's the thing. Just like with single linked list, the order matters of how you update this pointer. This is the worst case scenario. Not worst, but I'm like, the most complex one is when you're putting something in the middle, because before you only have to worry about 2 pointers, right? Now you gotta work, which are the green and the bright pink one. So this one and this one. Well, now you also gotta worry about, actually, no, sorry. Technically the blue one and the bright pink. Those are the only 2 you have to worry about. But now you got to worry about the green one and the purple one. So green and purple. So there's that. For deletion, the same story, right? So instead of updating 2 pointers, or sorry, instead of updating, I guess, 1 pointer technically, so like just skip all, you know, immediately to the worst case scenario. So let's say that you are going to undo this. So you want to delete the middle node here. The first thing you want to do is you want to back up into some pointer what you're about to delete. So, you know, go ahead and make a temp pointer and make it point to the node you're going to delete. Once you have that, then go ahead and start cutting it off by getting rid of this pointer right here. So make this point here. And then using temp next, preb, you can get to this pointer so that you can change it to point there. And once you've done that, you basically cut off the links to that node, at which point you can go ahead and just call delete on it safely, and you're good to go. Okay? So that's all there's to it. Yeah, that's it. So I'm going to code it for you, but before I do that, I want to make sure we're on the same page with a sorted linked list. Because I mean, I could just modify the code from last class and make it doubly. That would be cool. But we could also take this time to make a linked list that's a little bit different. This one's going to be a sorted linked list. So what is a sorted linked list? I mentioned it briefly last video, but I want to make sure we're on the same page. It means that it's going to be a list that's automatically sorted. So whenever you insert an unsorted item into it, which is any item, you just assume it's unsorted, it's going to insert it into the right spot. So think of like a deck of cards. So imagine that you organize like half of a deck of cards. By organize, I'm saying you sort them in ascending order. Then from the unsorted section, you take one card out, and then you are going to put it into the sorted section, but you're going to put it in the spot it belongs. So like maybe you have a 4, and you currently have in the sorted area like a 1, 3, 8, 9. So the 4 is going to go after the 3, but before the 8, right? So you're sort of sorting it as you go. In a way, this is what's kind of known as like an insertion sort algorithm, and in 302, you're going to learn all these different sorting algorithms. It's not really the point right now. The idea is that as you insert, you're going to basically look for where it goes and put it there. And so it's always going to contain a sorted sort of state. So how do we do that? Well, it's still the same code really from like a normal linked list. The only difference is before we were inserting at a specific index. In this scenario, instead of inserting at a specific index, what we're going to do is we're going to look to see where this should fit. Right? And so we still have the same 4 cases, like list is empty, inserting at the beginning, and the middle, or at the end. But rather than us picking which one we're going to insert at, it's just strictly going to be picked upon where the number belongs, or where the whatever. It doesn't have to be a number, but you know, usually you think of sorted things like numbers, but it could be letters too. So like if I have something like this, and I'm inserting a 0. Well, that has to go in the beginning. So I guess that's an example of inserting at the beginning, right? If I have an 8, then that's an example of inserting in the middle because it's supposed to go here, right? Let's say that I am inserting a 10. Well, that's going to go at the end. But how do I know it goes to the end? Well, I don't have the ability to see everything. Well, that could have gone really badly if the water opened on top of the computer, but it didn't. But yeah, what I can do is like, as a human, I can just see these numbers all at once and like be like, oh, well, that goes here, right? Computer can't really do that, and you couldn't either if you had like a million numbers in here. You have to look at each one independently, or a group of them if you're a human, and find out where it goes, right? So like, it's like if I said look up a word in the dictionary. You can't just like instant find it. You have to, you know, look around, and yeah, you can jump around, and then you know you open the half and do the other half and so on, which is an algorithm you learn in 302 actually. But there's a searching mechanism that you have to do, right? And so we have to code that in for the linked list to work, the sorted linked list. And that mechanism is you're basically going to start at the beginning, and you're going to look at each element, and then because you already know that what you have in the linked list is sorted, because every time you insert something is sorted, you can make that assumption that the list is sorted. And so as you're inserting, you can just compare what you're inserting versus what you're looking at. So I'm going to be looking at this 1 and this 10. The 10 is bigger than the 1, so it has to go after. So it cannot go before. So basically, you're going to look throughout the list until you find the number that is bigger than it. Because if, let's say you find a 15 here. If I find the 15, it means that the 10 has to go before that. But if you know, as I was going along, I must have reached this because everything else was smaller than, so you know it goes there. Another example, so like let's say you were looking at you had a 7. So you look at the 1 and the 7, 7 is bigger, 7 is still bigger, 7 is still bigger, 7 is not bigger than 8. So bam, at this point you know that it has to go before this 8. And because you got here by comparing anyone before it, you know that it has to go right in between. So as long as you keep that simple rule in mind, you'll have no problem sorting this. The other case, I guess, if it's the biggest number, is going to be like you compare every single number and then you reach null. If you reach null, it means that every single number was smaller, so then you know that it just goes at the end. Okay, that's it. That's all there's to it. So it's a pretty simple like logic that we're going to be coding in. The tricky part is just setting up the doubly linked list correctly. Okay, so that's all I wanted to say for like the prep. I think now what we just have to do is just get in there and start coding it. So let's do that. So here we have the code from last time. And this code is for the singly linked list. Sorry, really dry weather. And so I'm going to probably start from scratch because modifying code is cool and all, but it also takes a long time to do. So I don't want to do that. So maybe I'm going to leave the print function. The print backwards, you know, that was Nobel and whatnot, but we don't really need that right now. So I'm just going to get rid of that completely. And yeah, all my insert and delete, like we don't really need a special delete function because our delete is just going to be like our deallocation. So, and really the only difference between like I said, is just for a delete at a specific spot with the double linked list, it's just making sure you update the pointer. So you all can figure that out. Maybe we'll do a delete number. So it searches for a number to delete. And if it finds it, it deletes it. So yeah, we could do that. If the video doesn't go too long, we'll do that. This get PTR, all this stuff is nice, but like really, it's just much easier if we just do it from scratch. So yeah, we'll get rid of all of this. So the only one we're gonna leave is going to be the print function because that actually can come in useful to print. And yeah, we could code it again, but really it's just easy. And then we're gonna get rid of all the stuff in main. And conveniently, we're going to call this a doubly linked list class. Okay. So yeah, DLL. Okay. So yeah, let's just change the name of this to Doubly, and then get rid of all of these things. Keep the print function. Definitely get rid of the operator overloading and keep those two nodes. Okay, so yeah, we pretty much got rid of just about everything except the print function because this makes it easier to keep that in there. Let's just change this to doubly. Okay, and as you guessed it, we are calling the class doubly linked list. We do need to modify our node class, right? Because now we have more than just the next pointer. We have 3 components. We have the data, the next pointer, and then the previous pointer. So let's just throw that in. There we go. So now we have next and previous. Our constructor for the doubly linked list class, we want to initialize everything to null. So it's already head and tail set to null. So actually, yeah, that's all set to go. Oh, the here, that's what I was thinking. What we want to initialize is this previous pointer. We also want to initialize it to null, right? Just to avoid bugs. So yeah, that pretty much sets up our node class, and our doubly linked list class is basically up and running. This is good as is. Like, it doesn't matter that it's a doubly linked list. Traversing it, we can still just use one of the pointers. So yeah, that'll be good to go. So yeah, we are pretty much ready to go. So the first thing I want to do is an insert function so that I can actually test this stuff. Obviously, our print function has been tested, so we don't need to really do anything there. So yeah, let's just go ahead and do an insert. Our insert function is pretty trivial when it comes to parameters because what we're just going to pass in is what we want to insert. So a piece of data that we want to insert. And because we are going to insert it wherever it's supposed to go in the sorted linked list, We don't need to specify an index or anything. We just say this is what we want to put in, and then you figure out where it goes. And we are happy to accept that. So let's get rid of that. Actually, yeah. So yeah, we got to do the 4 cases that we want to insert. So, you know, in the last, with the single linked list, we did this get pointer function that was super cool. This time we're going to do it more traditional, which is I'm just going to do all the work inside of the insert function for all 4 cases that we have. And again, the 4 cases are list is empty, and then the other 3 cases are that the list is not empty, but you're inserting at the beginning of it, at some point in the middle, or as the last element in it. Okay? So let's go ahead and kind of do this in this order. So the first thing is, if head is equal to null, then we know that the list is empty, right? So if it's empty, then that makes life easy because all we got to do is just put it at the beginning and set the head and tail, right? So the one thing I want to do actually up here is I want to make a pointer, again, that temp pointer that's going to hold the temporary node while we figure out where it goes. And I'm going to just make that already as is because we're going to need to make it whether we're inserting in the beginning, middle, or end, right? So I might as well just have it ready to go. So the node has been created. Both the previous and the next pointer are set to null. So I don't need to worry about that. And if it has the data that it needs. All right. So yeah, let's go ahead and insert if the list is empty. So I just need to set the head and the tail both to point to the new node. And the new node does not need to change any pointers because it's currently the only node there. So yeah, that pretty much solves the issue of the node being in the beginning. Otherwise, you know, I could do an else clause like this and make it prettier. But to avoid, you know, wasting space, I'm just going to put a return statement so that I don't need to tap things. Okay? So yeah. So otherwise, think of it like an else right here. What I'm going to do is I'm going to start looking to see where this node goes. Okay? So I need a while loop for that. And that while loop is going to have to use a temporary pointer, which I'm going to use cur. So I'm going to make a pointer and I'm going to call it cur. And I'm going to initially have it point to the head of the linked list. Why the head? Because I want to start searching from the beginning. If I was doing like a descending order list or something, I guess I could do it from the tail, but that's kind of weird. So we're going to stick with the head. All right, so yeah, we're just going to say something like while cur is not equal to null, we start looking, okay? So start looking where this node fits. So how do we know that we reached the spot where it's supposed to go? Well, if what we're looking at is the node to insert at, like if the node's value that we're looking at is less than what we're trying to insert, so temp data, that means that we should insert right here, right? So if, it's like smelling, my dog's smelling something, it's like shaking, she smells. Interesting. So yeah, so if what we currently contain, if current data, which is, oh wait, no, not current, sorry, no, sorry, come down here, okay. So if the node we're looking at, which initially is the head node, if that value of that node is less than what we have, it means that this node should go after it, okay? If the node that what we have in front of us is greater than what we currently have, if the one we're looking at has greater value than what we have, so like if we have a 5, if we're trying to insert a 5, and the node we're looking at is a 10, then we should put our 5 before it, right? And if the node we have is a 5, and the node we're looking at is a 2, it means that our node has to go somewhere after the 2. It may not go immediately after, because there might be like a 3 and a 4 before a 5. So the only time we can make a decision like this is where it goes is only when we see a node that is bigger than ours, okay? So let's go ahead and actually do that first. So yeah, let's say that that what we're looking at is smaller than what we have. Okay, so node we are looking at is larger than what we have, so we have to insert it before it. Okay, so in this case, because we have to insert it, we start to update the pointers. So first, remember, we're going to have to update temp next, we're going to have to update temp prev, and then we're going to have to update 2 more pointers potentially for the node before it and the node after it. Okay, so what's going to be the node after it? Well, that is going to be cur data, because that's the one that's bigger than us. So cur previous should be updated to point to us. And then the node before current is going to have to, so node before current, if it exists, should point to us, should point to temp. That's going to be the tricky line, okay? That's why I'm putting a comma. But let's go ahead and do them in order. So temp next here, that's easy. That's just going to point to cur. Temp prev is going to point to whatever before cur, so that's whatever cur prev is currently pointing to. So this is where double linked list becomes useful. We can just very easily see what the node before the one we're looking at is. Cur prev, whatever this is containing, so the node before it, this should point now to us. However, actually, cur prev, is that what I'm really thinking here? Yeah, cur prev. So current previous means the node after us, the pointer that is pointing back to us. So think of it this way. This is cur. This is temp, and then we have some node after it, and some node before it. So this one doesn't really matter for now, but just imagine it. Okay. So the first line, temp next cur, is basically saying, okay, go ahead and make this point here, because this is what we're trying to insert to. We're trying to insert in between these two. Okay. Temp prev says take this pointer and point to this node here. Where is that located? Well, cur prev is this pointer right here, which means that that's going to get us here. So that's why cur prev gets us to that pointer. Okay. Now that we updated the pointers for temp, what I need to do is I need to take this pointer and make a point to that node. Let's pick a different color because that's kind of weird. I need to make a point to there. Okay? So I need to make that pointer point there, and I also need to make this pointer here point there. So let's look at that one first. This pointer is cur prev. So I just need to make cur prev point to temp. So that's line 36. The tricky one is this one. So let's take it step by step. How do I get to this spot right here? Well, cur prev gets us this item. And then to get the next pointer from that, I just gotta add next. And if I do that, then I get this. And that's what I need to update to point to temp. Okay? So that's where that line comes from. It says temp right there. Y'all can't see it. Temp. So yeah, that's the trick. So cur, prev, next, temp. Although actually, I should leave this comment. Cur prev next temp. There is a catch to this, and I put it here. If it exists, right? It's possible that the node before it doesn't even exist, which is not an issue for line 35, because if it doesn't exist, then all this is copying is a null pointer, which is okay. You're copying null to null, whatever, big deal. Similarly here, you're updating current node, so not an issue. This is the one where you're updating the node from before, and it may or may not exist. So if it doesn't exist, you definitely you don't want to update it, right? Because it's out of sec fault. You're dereferencing a null pointer. So to check whether it exists or not, we can just put this in an if statement and say, if cur prev is not equal to null, okay? What happens if it is equal to null? If it's null, this is the first node, right? And so that's actually useful to know, because if it's the first node, then we probably want to update. So take this comment actually, put it here. So if it is null, then because it is the first node, we want to update the head pointer to say that, hey, this is actually the first node now. We're reinserted at the beginning of the list, basically. So we should probably say head gets temp. And tail can stay as it is, not a problem. Okay? So that takes care of inserting basically at the beginning, but also at the middle. And now we only have to worry about inserting at the end. How do we know that we have to insert at the end? That's because we reached null at the end. So if we ever, oh, and I guess also I love doing this, so I gotta make sure I don't do this. After we finish inserting, go ahead and return. We're done at this point. Okay? Otherwise, bad things happen. So now, assuming that we're still in this function, after the while loop, so down here, we're only here if we didn't find a number larger than temp, right? It doesn't have to be number, but you know what I'm saying. Whatever we're comparing. So in this case, that's when we're inserting at the end. And so inserting at the end, and yes, we lost this pointer because it's now null. So if it was a single linked list, this wouldn't work. We'd have to either retraverse again or have to keep a previous pointer that we can then access. So like I could make a previous pointer in this line, and then at the bottom of this while loop, say something like prev gets cur, and then just keep doing that over and over again. Oh, by the way, that does remind me, I should put inside of this loop cur gets cur next, otherwise we'll never advance, right? But yeah, I could have this prev gets cur line and then keep a previous pointer so that after the loop I can insert that way. But this is a double linked list, so I can take advantage of that. So all I really got to do to append at the end is just use a tail pointer. So whatever tail is pointing to, I'm going to say tail next is going to get temp. And then temp previous is going to get tail, because that's the old tail. And then those are really the only two pointers that I got to worry about. So now I just got to update tail. So now tail is going to be temp. And there you go. That's it. That's how you take advantage of having a tail pointer and a double linked list to be able to insert at the end without having to have this previous pointer that we keep track of. So we should be good to go now. Like this whole insert should work. Obviously we don't have a delete, so it's gonna have a memory leak. But we can code that really quickly. Let's add a destructor here. And for the destructor, all I really gotta do is say like while head is not equal to null. Because it's a destructor, I don't care if I modify head. So I can just say, let's just use tail temp, because whatever, so I don't have to make a new pointer. So I'll just say tail gets head, and then I can say head gets head next, and I can say delete tail, and I just do this over and over again until I'm done. So yep, that's it. This will make sure that it deallocates at the end, so we have no memory leaks. Notice that I'm only using tail here because that's just a pointer that I can use. But I could also just like, if I wanted to make this cleaner, I could just make a temporary pointer and say something like no t gets temp, and then that gets head or whatever. And then I could say like delete temp, right? The idea is not to use a dangling pointer. So this works too, but I was using tail because like we don't need it anymore. And it's a good idea to not leave any traces behind for people to mess with dangling pointers. So even though this is in Destructor, it's still better to play it safe. Okay, so yeah, we should have any memory leaks now. Assuming the code works, you know, we might have bugs. Let's see what doesn't compile right now. Oh, well, we need to have Doubly. I always forget that linked list in here. That's the first kind of important thing. And okay, yeah, it's working. So obviously we got to test to make sure that the inserts are done correctly. I'm not guaranteeing they are. So let's just try inserting something like a 5. So this will test the case of inserting with an empty list, right? There we go. It works. Cool. All right, let's try inserting at the beginning of an existing list by inserting like a 2. Ooh, that one didn't work actually. Let's see what happens. Let's run it with a debugger. Okay, so make the node. Node cur gets head, while cur is not equal to nor. If code is greater than data, it's it is, so it should go in. Temp next gets cur prev gets temp prev gets cur prev, which is null. You can see that being assigned to null there. Cur prev gets temp, which is a null pointer getting a value. So we'll see prev getting value there. So this line will change. It did. Okay. If cur prev is equal to null. Oh, ooh. Maybe this line and this line should be flipped. Yeah. So this line should probably happen after this line, because what this line is doing is, you know, as we're inserting at the beginning, so we have this, right? So cur prev is updating this pointer. This is cur, and this is temp. So cur prev is saying update this to now point from null to the new node that we're inserting. But then now I want to see if a node exists before this one. I'm trying to update this pointer to point there, but I just overwrote that pointer. So you can see how that would be a problem. So this should happen after. Yep, so that should fix that issue, or at least it should fix a issue. I don't know if that'll be all the issues fixed, but yeah. We can see that the 5 works and the 2 works. Let's just run the 5 alone again, just so you can see that. See, 5 works, and then inserting something at the beginning. See, debugger, like, it would have taken us like 20 minutes to find that issue if we hadn't used a debugger. So again, I keep preaching debugger because I know a lot of you don't use it. You're shooting yourself in the foot, trust me. Embrace the debugger, it's meta. Embrace the meta, okay? Now let's go ahead and insert something at the end, see if that one works. All right, that one works fine. Let's try to insert something in the middle, and that should be wrapping up all the tests that we need. So let's put something at 7. As you can see, oh, by the way, I guess the sorted part works too, as you can see that. So, yeah. Duplicates, that's one case that I haven't considered at all. What happens if I put a duplicate? Does it break? It seems not to be breaking. even though I didn't consider it. So I guess I got lucky there. But yeah, well, maybe the tail pointer is all broken. I have no clue. Let's try putting in a number bigger than 10, like 9. No, it's working fine. Do we have any memory leaks? Let's see. Ooh. Relax, relax. There we go. Let's get rid of this, by the way. There we go. Nope, no memory leaks. So the destructor is doing its job. So there we go. We got all the insertions working. So, and we got all the deletions. So really all now we need is like maybe a way to remove a number. So like remove the number. So search and destroy kind of thing. Okay, so let's just really quickly code that in. So, and that'll be pretty much the last function I want to do. Actually, you know, one other thing that could be neat to show you is a backwards print without recursion by taking advantage of the double linked list. So let's just do that really fast. So I can say something like while, so make a pointer node t temp gets tail, so start from the end, and then say something like while, actually hold on, let's just do this outside the function. The destructor I'm okay with leaving inside, but the other one I'd rather have outside. So let's do something like template class t void, and then what was it called? Backwards print, lowercase, uppercase, lowercase, backward print, backwards. What's the? I don't know what the correct like grammar of that would be or spelling, but whatever. We'll do that. Backwards. Let's Google. Backwards. Backwards is a word, so I think we need the S. So we'll go with the S. Leave a comment below if you're actually a native English speaker, what the correct thing is. Yeah, okay, so the loop is going to be like pretty much what we have already here. So in fact, let me just copy paste this. The only difference is instead of head, I'm going to make tail. And instead of cur next, I'm going to make cur prep. And we can keep the arrows the same. In fact, since it's a double linked list, I guess it makes sense to have a dot in front and at the end, right? Oh, actually, we want arrows in both directions because that'd be kind of cool. So maybe like that would be fancy. And also we want to do that for this one too. To better like indicate that this is a double linked list. Like, upgrades. I will never learn. Well, you will, right? Okay, that looks way too cluttered now with the arrows. I regret doing that at this point. Yeah, I mean, it's okay, but it's just like, it hurts my eyes. So, no double arrows. Okay. DLL backwards print. 9887752. This is also good because it makes us it's checking to make sure that the previous pointers are working. So I'm not just doing this for fun. It's actually useful to make sure that the linked list previous pointers are working. Otherwise, we could just have a broken double linked list that's really just a singly linked list. But you can see it's working. So yeah, that's fine. Okay, so as you can see, the only magic is we start with the tail instead of the head, and instead of going cur next, we go cur prep, and you're good to go. All right, so now, like I said, the last thing we want to do is the delete, and we are on track. We got half an hour, so we should be able to achieve this. So the delete is going to not be called delete because it's a reserved keyword. So delete, search and delete. What looks nicer? Search, delete. That looks better. Yeah, we'll go with that one. I'm not gonna forget it. I'm not gonna forget it. There we go. Yay. Basically, what the search delete will do is it's going to search the linked list, and basically, if it finds the number you're looking for, then it'll delete it. If it doesn't find it, then it's not going to do anything. In fact, that sounds like a good job for Boolean. So we can make it return true if it deleted and false if it didn't delete anything. Okay. So let's change this one to Boolean. Very cool. Okay, so like this is a hidden function in the sense that like all this is going to be is like it's going to be almost the same as the delete app function that we did for the singly linked list, because we have to consider all cases: empty list, beginning, middle, end. So yeah, and also deleting the only item in the list, which then becomes empty. So we got to consider that as well. So it's still a bit of work. So if you thought like half an hour for a single function would be like easy, yeah, we'll still make it, but it'll take us a good 20 minutes probably to debug it if we run any issues and things like that. So yeah, let's get going. Let's start with the easy stuff first. So let's just say that the current list is empty. So if head is equal to null, empty list. So that's nice because all we gotta do is just return false. Can't delete whatever doesn't exist, right? So there we go. Again, I could do an else, but I'm gonna keep it clean by, in fact, I'm even gonna get rid of these and just do it like that. Empty list. Okay. The next case scenario is deleting from a list that is not empty. So I'm gonna add a special case here so I don't have to worry about it later, where the head and the tail are the same. Okay? If the head and tail are the same, it means there's only one item in the list. And if that is the case, let's just see if that's the one we gotta delete. So if head and tail are the same, and obviously head is not null because otherwise it wouldn't gotten here. So head data is equal to data, the one that we want to delete. Then in this special case, it means that we have single item and deleting it. In that case, I'm gonna go ahead and say delete head, and then go ahead and set head and tail to be equal to null. Okay, so that takes care of the special case where we're deleting the only item in the list. I could handle this elsewhere. I'm just trying to make my life easy to not worry about it. I might come back and delete this code if the code I write needed to handle this special case. But I just want to make sure I don't screw up the tail and the head pointers. So, yep, do that, and also return success. Okay, otherwise, I don't want to forget this. I'm going to say return failure, and now we can worry about trying to delete from a list when after we finish deleting, it will not be the last thing that we deleted. So for that, I'm going to set up a temporary null pointer, as I've been doing so far. I'm going to call that cur. I'm going to set it to point to the head. And now I'm going to say, well, cur is not equal to null. If I ever reach null, it means that I reached the end and didn't find anything to delete. So I can go ahead and return false after that. Okay? So let's just basically, it's kind of like the insert, but kind of reverse again. So we can say if cur data is equal to what we're trying to delete, then that means that we found it. So we found something to delete. Now, also we got to make a decision. do we want our search and delete function to delete the first instance that it finds, the last instance that it finds, all instances? I'm going to go with delete all instances because that's cool. We can delete multiple duplicates, you know? So like, for example, here, if we say delete 7, it should delete both of the 7s. So for that, it's a matter of adding a return statement in here. If you wanted to delete only one case, at the end of this if statement, you could just add a return. Otherwise, or you just let the loop keep running. And then eventually it'll end when it stops finding duplicates. Although, then it'll return false. So we might need to modify, we might need to add a boolean up like, hey, we returned something. So yeah, I'm gonna do that. So bool, deleted something. I'm gonna set that initially to false. And then here it'll be set to true if we actually do delete something. And now instead of returning false, I'll say deleted something. Okay? So that handles the Boolean system still working and duplicate deletion. Okay, so if we do find something to delete, again, we could be in one of 3 cases. We could be at the tail, at the head, or at the middle. So let's just start by thinking about the, let's not even think about it. Let's just do like if we were thinking of the middle one. Okay, so what we're gonna have to do is we have to update cur next. Actually, cur next and cur prev are being deleted because cur is being deleted. But what we need to update is whatever's after cur next. So whatever is there, the previous pointer of that, so the next node to the one we're looking at. So I think we need picture time for that. So let me draw what we're dealing with here. So this is cur, and it's what we want to delete. Okay, we want to delete this right here. So we're going to have to do a couple of things. We need to update the following pointers. We need to update this pointer, and we need to update this pointer. Okay, let me actually go with a different color for each. We want to update them as follows. We want to make that one go from currently pointing to cur, and we want it to point to this one. And then we want this pointer from pointing to cur to point to the one before it, okay? And then of course, then we can just go ahead and delete cur afterwards. So how do we get to those pointers? Well, this is cur next, and this is cur prev. So if I say cur next prev, then I'm going to get this. Because remember, this is technically cur next right now. And this is cur prev, or at least what cur prev is pointing to and cur next is pointing to. So if I say cur next prev, then I'm able to access this. So that's that pointer. And over here, if I say cur prev next, then I can access basically that pointer. Okay? I don't think that's the same color. Maybe this one. Yep, this one. Okay? So those are the 2 pointers that I gotta update. And once I update those, then I can go ahead and call delete on cur. So cur next prev is the first one, and then the second one is cur prev next. So what do they have to point to? Well, remember that this is cur next, so I just need to make the green one point there. So all I need is to make this point here, and that's actually currently at cur next. And for the one up here, what I need to do is make that point to the one before it, which is at cur prev. You might have to like rewind the video and watch this little piece again to like so that it really clicks in as to why this is the case. Okay, it's okay if the first time it's kind of weird. Is this what you thought you'd be doing when you first learned pointers? Welcome to the real world, I guess, or whatever. Okay, so yeah, those are the two lines, cur next and cur prep. So cur next prev is going to basically have cur prev and cur prev next is going to have cur next. Okay, as long as you do those two lines, I think this is probably the hardest lines that when you think about linked lists, that's going to be as hard as it gets. And then delete cur. Okay, so this will handle deleting stuff in the middle, but there are problems. This line of code right here may not exist because if there's nothing after cur next, so if cur was the last node, this will segfault. Similarly, if there's nothing before the node that we're deleting, because it's the first node, that will segfault. So we're going to have to wrap these two in if statements of each of their own. So I'm going to say if cur next is not equal to null, then try doing that. Otherwise, don't do anything. And the reason why I don't need to do anything is because it would already be pointing to null, so no need to update a null with another null. Similarly over here, if cur prev is not equal to null, then go ahead and try that. Otherwise, don't do anything. And what happens if there's nothing before and nothing after? That means that's the only node. So then you would just go ahead and delete it. And that would work too. But there's other things we need to do here. And that is that if the case is that the node is the first node or the last node, we also need to worry about head and tail. So in this case, if this is equal to null, or I'm saying if it's not equal to null, sorry, if it's equal to null, then it means that it's the last node, right? So we can say equal to null, so it's last node. If that's the case, that it's the last node that we're deleting, we need to make sure that we update the tail. Right? And similarly over here, if the previous node is equal to null, it's the first node. So we need to update the head to the second node. So how will we update the head to the second node? We would say cur next gets, or sorry, head gets cur next. Right? That takes care of that one. Similarly over here, we can say tail gets cur prev. Right? And that will get us, that will point the tail to the one before current so that we don't have a bad tail. So yeah, that should basically do it for us. It only took us about 15 minutes. Well, we'll see though. We'll see if A, it compiles, and B, it works. So let's try it. So we can comment this out, the backwards print, so it doesn't confuse us for now. Let's try to delete stuff. So again, we're going to delete in order of like that we care about so that we can see if things are working. So let's start by deleting the first entry in the list. So let's try deleting the two. Oh, and I guess let me. We have. I think we have an infinite loop. So we already have our first bug. Let's throw in a breakpoint. Okay, so let's see if search and delete 2 will work. So See if it finds it too. Ah, crap. Hold on. Run it again. Enter. Okay, so head is equal to null. Nope. Head and tail. Nope. Okay. Delete. Okay, so here we go. Oh. Forgot. Big thing, right? Don't forget. When you finish doing all of this, you need to do cur gets cur next, right? So it advances. Otherwise, it's just checking the first one repeatedly. Although, this does remind me of something. When we delete cur right here, that's technically accessing a dangling pointer. It's not a good thing, right? So, as we have it right now, there's some dangling pointer nastiness going on. So, maybe to avoid a dangling pointer, I'm going to make another pointer. So, fix pointer problems with more pointers. Always a good thing, right? Can't call it temp because I'm using temp already, so I'm just gonna call it temp2. Oh, that's a weird name. Cur2. Cur2 is going to contain. How about actually we can call it next. That won't conflict with the local variable. It shouldn't. We like the member variable. But to be safe, we'll call it cur next. Okay? And cur next is just going to contain basically cur next. So that way here I can just say cur gets cur. What's it called? Cur next? Why is it not showing up? It is just called cur next. Okay. Oh, because I put it inside of the if statement. There we go. Okay, so cur next is basically the containing the next pointer that avoids dangling pointer nastiness. Also, it makes sure that when we delete a node, we continue off of the next node that was available. Okay? Yep, that should be okay. Yay, it didn't check one. Okay, and it worked. It did delete the 2. So the 2 has been deleted. All right, let's try to delete the last item. So let's try to delete the 9. And it deleted the 9 successfully. Also, let's try to print backwards because to see if things broke when we deleted things. Nope, they didn't break. Okay, now let's try to delete something in the middle. Plus, we get to see if the duplication works to delete duplicates, because we'll delete, let's see if it deletes both 7s. Ah, look at that, it worked pretty well. All right, very cool. Let's try to delete something single. So let me try inserting a number between them and then deleting it. So let's try to insert something like a 7, and then immediately delete it afterwards. Yep, works just fine. So we tested before, we tested after. Let's try to delete both duplicates again. Oh, actually, you know what? No, let's try to delete the 5 and then delete the 8. See if deleting duplicates when it's the last thing breaks it. That might actually break it. I don't think I've considered that case. Oh, I didn't break it. Interesting. I thought it would. But it didn't. Okay, let's try flipping the order of these. Let's try to delete the duplicates first and then delete the solo. So that should leave only a 5. And then if I run this, and then let's try to insert something into it after we delete, just to make sure that it is actually okay to still insert. Yeah, and then one more time, let's flip these just to make sure. Yeah, it still works. So yeah, one bug, but we had it otherwise. Let's see if Valgrind is happy with us. Yep, Valgrind is very happy with us. And we are happy with Valgrind. 137 lines of code, not bad. So, yep, that is it for linked lists and this class. You probably revisit them in 302. So to summarize, what I showed you today is a double linked list versus a singly linked list. The big difference being that the double linked list has a pointer, a second pointer that points to the previous node in the list, which allows you to basically traverse in both directions. Very useful thing. You basically, this is kind of like a teaser of like trees and other things in 302, or graphs where you can have tons of pointers in one node. So this is kind of building up to that eventually, but it's a very kind of basic but important concept to have, this ability to have a node that points to multiple things. So it's not just like, oh, you know, single linked list, double linked list is like single linked list but like slightly better. No, it's not the reason we cover that. It's because it starts to kind of get you comfortable with a node being connected to more than one thing. Okay, and that's how trees are made. So, you know, it's like, well, can we have a linked list? And then linked list at home is like an array. You can be like, no, I can make my cool linked list by making double linked lists that are even better than arrays, because I can go in both directions and insert things in the middle. So, yep, that's it. We also saw the sorted linked list concept, which allows you to keep a sorted list. And by the way, we mostly just did integers, even though it's templated. But I could just as easily put it in like cars or any object really, as long as I overload that greater than or less than symbol. So really, this class that we've made, this template linked list class, is it's good to go for anything you need for it. So hopefully you coded it along with me and you just don't just take this and like use it, because you got to understand it. Otherwise, you're gonna get burned. So, but it is available for you on Canvas. So, yep, that's it. So the only topic that remains is going to be stacks and queues. And stacks and queues is another data structure that you can implement using a linked list or using arrays. So we're going to take a look at that as a final topic of this class, and then we'll be done with CS 202, and you move on to greener pastures in 302. So until then, thank you for watching, and I'll see you on the next video.